Every wireless ping and cloud upload relies on a massive, chaotic physical reality. If you look behind the walls of any data center, you will find a dense tangle of cables routing every single bit of data. The deliberate geometric arrangement of those cables, computers, and routing devices is called the physical network topology. It is the literal blueprint of how your hardware is connected. But having a physical connection doesn't dictate how data actually travels. That is the logical topology, the specific path data takes to move through that physical layout from one device to another. This diagram introduces the three foundational shapes that built modern networking: the bus, the ring, and the star. Choosing a shape for a network is a strict business calculation. You are directly weighing the upfront cost of physical cables against the long-term financial drain of network downtime. Every time you add a device to a network, you pay for physical infrastructure and the labor to install it. If you optimize entirely for the cheapest, simplest installation, you run fewer cables. That forces multiple devices to share the exact same communication lines. The problem with shared lines is that they create critical vulnerabilities. If one shared cable gets cut, multiple users lose their connection at the exact same time. To prevent that cascading failure, you need fault isolation. This is a network's ability to contain a physical break to a single machine, allowing the rest of the grid to stay online and productive. The best topology forces management to decide if the financial pain of an outage outweighs the upfront cost of dedicated cables for every device. This diagram illustrates the bus topology, where every device shares a single backbone cable. Data is broadcast down that main line to all nodes. Every device sees the traffic, but only the intended recipient accepts and processes the packet. Because it uses one main wire, the bus layout is incredibly cheap and simple to install for very small physical spaces. But as you add users, traffic scales up. Multiple devices trying to talk on that one wire at the same time create data collisions, which forces the network to halt and resend data, slowing everything down. Worse, if that main backbone cable breaks at any point, the entire network goes dark immediately. The bus topology serves as a legacy lesson in bottlenecks. It proves that minimizing your cable costs completely sacrifices fault isolation and operational stability. Here in this diagram, we have the ring topology. Devices are wired in a closed loop, and data travels in exactly one direction. To solve the collision problem of the bus, the ring uses a token passing method. A node can only transmit data when it holds the empty token. Since only one device talks at a time, data collisions are eliminated. This provides highly predictable data latency. Every device gets a guaranteed turn to speak, making it useful for specialized telecommunication systems. The trade-off is a highly rigid, fragile structure. If you need to add a new computer to the network, or if a single workstation crashes, the loop is physically broken and traffic stops. Preventing a total crash requires installing a secondary backup loop, which means paying for dual ring redundancy. While the ring organizes chaotic traffic, it lacks individual fault isolation unless you double your infrastructure budget to build a safety net. Finally, this diagram brings us to the star topology. Every single device connects via its own dedicated point-to-point cable to a central switch or hub. The central switch actively manages the traffic. Because each device has its own lane, the shared collision domains of the bus and ring are eliminated. This design provides complete fault isolation. If a cable is cut or a computer dies, only that specific machine drops off. The rest of the network keeps working. Providing a dedicated lane for every computer requires significantly more physical cabling than any other setup. It also requires purchasing centralized hardware, the hub or switch, to act as the brain of the network and process all those distinct connections. By centralizing the traffic, you create a new vulnerability. The switch itself is a critical single point of failure. If that switch dies, every connected device loses access. Despite that risk, organizations realized the cost of extra cables and robust switches is drastically cheaper than company-wide downtime and complex troubleshooting. That calculation made STAR the standard for modern enterprise networks. If we judge the bus, ring, and star strictly by their performance in real-world scaling, the trade-offs become clear. For cable efficiency, bus uses the least wire, while star requires the most, earning a red X. For fault isolation, bus and ring fail, but star successfully isolates individual hardware failures. For scalability, star handles heavy traffic seamlessly, while bus clogs and ring requires workarounds. Network design has overwhelmingly abandoned shared physical mediums. Dedicated pathways are simply more reliable. The industry collectively decided that effortless troubleshooting and limitless scalability are vastly more valuable than saving money on copper wire. In the real world, avoid the bus topology completely. You will only encounter it if forced to maintain legacy industrial manufacturing equipment. The ring topology is strictly for specialized telecom or automated environments, where rigid, predictable traffic control is far more critical than physical flexibility. That leaves the star topology as the absolute default for most modern applications, serving everything from your home Wi-Fi router to massive office LANs. This technical diagram illustrates how modern enterprises handle massive campuses. They link multiple star networks together into hierarchical trees, connecting lower access layers up to a core backbone. Ultimately, a network's topology serves as the physical manifestation of how much a business values its own uptime.